Hello, good morning. I'm Alex Black and welcome to this ASE special COVID webinar. Before I start, I would like to thank the ASE communications team who've worked with me and I think all the presenters prior to and after each presentation. So a big thank you to Angela, Catherine, Emilia and Alistair. And also a big shout out for the ASE in general. It's been a mainstay of support for me and ideas throughout my teaching career. I've been going to the conferences for the last 5 years. It's one of the most fantastic set of events you can imagine, and some of the greatest networking, as well as being the biggest subject association for science education in Europe. Okay, today's webinar is about CASE and how you can develop lessons that bridge from the CASE methodology. It's going to be split into 4 parts. The first part of about 20 minutes on cognitive readiness with up to 10 minutes questions. Second part on cognitive demand, again followed by specific questions. And then the final part will be looking at how to apply this cognitive readiness and demand and the pedagogy of CASE into other areas of the curriculum. And I'll be showing some of the bridging lessons that we've created, and that'll lead into final questions. Also, you can see the bit.ly link. You can download this presentation, so you have all the links and all the references. Okay, so to get clear, what is CASE? Well, at its minimum, you can think it's the 30 original intervention lessons, and I'm stressing that. They were designed to intervene in the development of students' scientific thinking and to try to accelerate the development of their ways of thinking, this Piagetian schemata of thinking. And this was done traditionally in the first 2 years of secondary schooling, which would be year 7 and year 8 in the United Kingdom. Though there have been some variants. In Ireland, they did it across the primary secondary transition, and in some other countries, it's been done later in secondary schooling. That's the bare minimum, 30 lessons designed to develop thinking. However, it was based on many decades of research, and I'm going to give you a brief overview of some of that in terms of developing a theory of the readiness of students in their thinking and the demand of the secondary science curriculum. And this was first published in this book, Towards the Science of Science Teaching, in '81, when I was doing my PGCE at Leeds University. And people in the 19th century write about how reading The Origin of Species changed their lives. Well, this changed my teaching life. And so it's a theory that's been put into sets of lessons shown on the left, that have a readiness to start students at a lower cognitive demand and then target a higher and an even higher. And the whole idea is to stretch the cognitive demand throughout the lesson and to lead the students to stretch their thinking. Okay, so this idea of cognitive readiness, the authors of the CASE program, Philip Adey, Mike Scher, Carolyn Yates, they were particularly informed by Piaget and his description of how students go through concrete operational thinking to formal operational thinking, and they use Piagetian terminology. Now, up to 1974, and this came as a big surprise to me, the age of transition in these stages was rather over-optimistic, and we'll see some of the data about that. This was done with smaller samples, and it seemed quite biased, more advanced thinking students who were related to the researchers in the Geneva area. For instance, the fact of students from 11 to 13 moving into formal operational thinking is very, very over-optimistic. A key for me in understanding Piaget is that it gives access for me as a teacher and for teachers in general to get to know about student thinking and how student thinking affects their learning, especially of the quite strong conceptual demands of many science ideas. Now, Dylan William and John Hattie agree on very little, but from their writings that this is one thing, that if teachers and students become aware of how they're thinking and how they're learning, this is where we can have quite a big impact. So the CASE people at Chelsea College, which then later moved into King's College, they worked, and they obviously had some good government funding, to change the Piagetian clinical interviews that were done around scientific phenomena and everyday phenomena. They developed these as science reasoning tasks, SRTs. They developed 7 of them, and the first 4 are the ones that I've used throughout my teaching career. In fact, just about all the students I've taught at different age groups, I've always, to begin with, the first lesson I've had them, I've used one of these SRTs. The ones with the green, you can click the hyperlink and get the whole package, the original test, and also some scoring sheets, and also the teacher instructions of how to deliver them. And that was important, that all of the research that the CASE project did was designed that it would be helpful and produce tools that teachers could use to help their students' thinking develop and to help them get to know their students' thinking. So these are group tests that can be used, and they're very similar to a CASE science lesson. You show some phenomena and you elicit some responses from students. They validated these with the usual kind of psychometrics, internal consistency test, retest correlation. They especially wanted to make sure that these group tests were replicating the same kind of cognitive measurement as the interviews. Also, they were looking at the claim that the Piagetian theory made was that formal operational thinking develops as a unity. And they put this to the test using factor analytical models, and they were largely satisfied that they had evidence for that, except a very interesting anomaly was produced, which was combinatorial reasoning seemed to be a more advanced form of thinking than had been uncovered by Piaget and his co-workers. Now, that was a very interesting anomaly for me, later teaching IB biology, teaching genetics, for instance, where you move from monohybrid to dihybrid crosses and Hardy-Weinberg. It helped me to understand that I needed to scaffold and structure students' thinking, because combinatorial reasoning seemed to be a package of challenges. So this is where research can be highly informative for teaching practice. This is a summary, and I'll look in more detail of the results they found. And the alarm bell really is that in the final years of GCSE or O-level at this time, the mean of students hadn't yet reached formal operational thinking. Now I'm going to show you how, briefly, how one of these tasks works. This is probably the most used in research, and I've used it with thousands of students actually over my 37 years. And it's called volume and heaviness. And just to give you a taste of it, the diagrams you see in the test, the students have them as, I used a Google form in the old days, used a paper and pencil. You actually demonstrate exactly what's there. So the measuring cylinder A will be filled to 100 milliliters in front of all of the students, pointing out that you are filling it to 100. Then that will be poured into beaker X, and then you will refill beaker A. And then all of the questions tend to be categorical and discriminatory to uncover whether a student has an idea of conservation of volume. And staggeringly, many year 7 students, more than you'd think, actually think that somehow there's a change in volume taking place. And This test then has items that slowly climb cognitive demand. And for instance, same thing here, you show pouring 100 milliliters into each of these different volume empty vessels and ask them again whether they have the same amount of water. And then we're trying to explore, because these are designed, just as the clinical interviews, to elicit what concept and constructs students have in their mind to make sense of experience. And the popcorn one is you have corns that are unpopped, and then you actually physically pop them in front of the students. And again, ask categorical questions to see if they have a concept of the conservation of material or volume. Similarly, then we get to a plasticine block that we actually show them and give them the correct answer of that the block has 60 centimeters cubed when it's in a block form. And then there's a completely filled liter measuring cylinder, and then they're asked to predict how much will spill over when you lower the plasticine in on a fishing line. Then a slightly more advanced, where instead of what will spill over, it's looking at what new volume will be reached. And then this original block that anyone who conserves volume will think will have the same volume is rolled into a ball and then a cylinder. And this again discriminates those who are still struggling to have a concept of volume conservation. And then item number 10 is you have the plasticine block and an iron block of exactly the same shape and size. Pass it around the students, they can weigh each other in their minds, in their hands. And then the same question is asked, and what will happen if we lower the block of metal? Will it be more or less or the same that will spill over as with the plasticine? And then they're asked to explain their thinking. I found that usually 50% of year 7 students think that the metal block will displace more, even though it's perceptually exactly the same volume, because they have a concept of size that doesn't really differentiate between mass, volume, density. And then the later stages of the test elicit understandings of the concept of density. Often you find very, very few students are able to access this in year 7. And so it's discriminatory at the higher Piagetian level. Okay, so back to the results. That was an example of the group tests were performed with 11,000 students, a representative sample across the United Kingdom. And these are the results. And I'm going to focus on the 14 to 16 age group, which would be now the GCSE curriculum, to see that the readiness of the students at the start of that, the mean readiness, is at that kind of level, is still mid to late a concrete operational thinking, whereas the demands of that curriculum are in the formal operational area. And so we have a gap between demand and readiness. Anton Lawson in the University of Arizona produced, and you can click this link, this is a multiple choice classroom test of scientific reasoning that is very easy to administer if you can't have the time to use the group experimental tasks. It's a 2-tiered multiple choice where the students have to make a response and then make a response to an explanation of their first response. Now moving on to part 2, after we looked at how you can measure student readiness, and we looked at the gap between student readiness, in particular at the start of GCSE years. Now we will want to look at how Adi and Cher developed what was called the curriculum analysis taxonomy as a way of validly measuring the cognitive demand of key objectives of the science curriculum. To give you an example of this, the cat has lots of learning objectives that were current at that time in the Nuffield curriculum, and they were able to group them into early concrete, late concrete, early formal, mature formal. And I'm looking at temperature because, and heat, because these are some of the concepts that the bridging lessons in part 3 were about. And I've always found from the first time I looked at this that this was an incredibly informative mapping of the type of responses you would expect from students and that you would see in assessment items, in classroom conversations. And it gave really, really great insight into students' thinking again. And in particular, in planning the lessons that you'll see in the third part, the idea of how students conceived of temperature and heat was really, really useful in designing the lessons and designing the kind of talk and discussions that you would have with students to use and stretch and challenge their conceptions. In particular, the concept that a kind of maturing of their heat concept leads to a kind of substance view. This was well known to me from previous literature and my own experience as a teacher, but again, gives good guidance of the type of level of thinking that students are capable of and are currently operating at. And it also gives guidance into how to move the types of discussions and the concepts along, looking at, for instance, a more dynamical statistical concept of heat that relates to other concepts like particle theory. So that's just a taste of the many pages that are in Towards the Science of Science Teaching, which again, you can click the link and get from stem.org. Okay, so Shea and Ady wanted to test the cat, so they decided, well, what we need is, again, an instrument that is useful for teachers and curriculum designers, heads of department, and they worked together with these 10 heads of science who they trained in the Piagetian background, but they also wanted to see that if teachers who were not familiar with the Piagetian background, if they also could use the cat in a reliable and valid way. So what they did was they looked at the Nuffield science curriculum, and from 30 topics across all the different aspects of science, they selected 64 key conceptual objectives, and they turned them into assessment items. Then these items, they used to assess students who already had been grouped by the use of the science reasoning tasks into the Piagetian stages, as shown in the flow diagram. So they had a range of objectives that had been turned into assessment items. They worked with a large group of teachers and students, and then they were able to match the Piagetian level of thinking that the students were bringing to have a look at how demanding the assessment items were. I'll give you an example. This is an objective, very familiar to general science curriculum, the idea of purification of rock salt. And so we have this objective, and then they had some exam items, and for instance, some simple questions. What is the white product produced? Which is pure, the rock salt or the white powder? And now I want you, with the use of the poll, to do your estimate of this objective 42. The objective, not the exam items, the objective to carry out the experiment and realize that the product after evaporation in water is purified rock salt. I want you to rank him using the poll on a number scale from 3 to 9, as shown here. So 3 being early concrete operational thinking, 7 being early formal, 9. I want you to rank with the poll this learning objective. Okay, I'll give you 30 seconds for that. Okay, and we'll do the same procedure with another objective to interpret results in terms of the reversible process of salt dissolving in water that can be recovered by boiling off the water. So again, with the poll, I want you to make your estimate from a 3 to 9 along this Piagetian scale for objective 43. Okay, I'll give you 30 seconds. These are what the raters in this whole research group came up with, that 42 was a 2A and 43 was a 2B. Now I'll show you how they actually made that assignation. This is for objective 43, the one that you've just looked at. And you can see in the graph that they have the students at the different Piagetian levels and the relative success that they had in terms of the percentage of students who could make a correct answer to these. And as you can see, the students have been measured with a Piagetian level of formal operational thinking had the highest degree of success. And using item response theory and various psychometrics, the idea is that a 2/3 level would show the difficulty of this item. And so that item 43 had a score of 5.9 on the Piagetian scale. We'll see what that means now. These people work together in the psychometrics, and so the SRTs and the CAT had this input of some of the world's leading psychometricians in this area. Okay, you can see 43 where it occurs. It's at 5.9, which means it's just on the very last stage of concrete operational, and it's just getting towards early formal. Now, this shows a range of the objectives. Remember, there were 64 objectives. And what's happened is that the assessors, which includes the 10 heads of science and the 15 experienced science teachers who were brought into the project, made their estimation, just like you've done. And then we have the actual measure that's been the exam items using the item response theory. And there's a regression line, and this shows a reasonable validity, except something really interesting happened, which is there was a group of objectives that seemed to be an outlier on this regression line. A common feature they all had was that they were all based on the idea of model-based reasoning, of having a formal model. This would often be to have a model of what a solution was, or to apply a particle model, to apply a statistical dynamical model in thermodynamics. So they were all model-based reasoning, and these were actually very much more demanding. That was very, very useful information for me as a teacher. I'll give you an example, which is number 29. I'm sure many of you have done chromatography of extracting chlorophyll from leaves, using water and pestle, using sand to crush up the leaves, and then dissolving and getting a solution or a group of solutions extracted in acetone or some other kind of solvent. And then they would be worked through a paper chromatograph. And often you would see a yellow section and a green section. Well, the items, and then subsequent discussions I had with students, the items that Sharon had used, it was clear that many students who were not really having a formal model were thinking on these lines. And they would explicitly say this: the green comes from the leaf and the yellow comes from the sand. which shows that to fully understand this, you have to have the concept of there being a solution with solutions within it that have been extracted, and the chromatograph has shown them to be separate solutions. And so something that I thought is a very much hands-on, very visual, perceptual, actually is quite demanding of conceptual thought. There's a classic example. The two others you can see depend upon the reversible idea of water and the spongy nature of, for instance, when you're looking at expansion and contraction of gases with heating. So again, the instrument they used, the CAT, in their testing event, produced very, very important information, very useful to you as a teacher, to know that many objectives that you had thought were much, much less demanding were demanding of formal models. And therefore, that we would have to scaffold and match these in terms of our curriculum development. They, of course, were interested to see that the CAT was a reliable and valid instrument that could be used by newcomers. By newcomers, these are not new teachers, they're teachers that have been teaching science for a goodly while. But they got very, very good agreement between the experts, the trained committee, and the newcomers, showing that this CAT is a reliable and a valid tool to map out cognitive demands of the science curriculum. Now, time for questions. Okay, now moving on to part 3, which is where we're going to look at how I applied this cognitive readiness and demand theory to creating some what I call bridging lessons. This is again the 30 original case lessons showing the entry point to each lesson and its cognitive load, the target of the main episodes of the lesson, and some of the more stretching activities. And as you can see that throughout, when a reasoning schema, for instance, variables, is being addressed, there's a steady climb through the 30 lessons. But when a new schema is introduced, usually there's a dropping down of the target level. And this happens throughout the program. And this allows there to be space for progression. I thought that needed to be taken into account when I was designing lessons that would continue the case process after lesson 30. That would be into year 9. Now, the lessons that I developed that I'm talking about here are in the area of temperature and heat, thermodynamics, thermal physics. And again, this is information from the curriculum analysis taxonomy that Sharon Adey produced. And it gives a real focus of where to stretch students, especially when you know at what level they've tested it using the science reasoning tasks. And it gives real indication of how to push them up this conceptual level through the idea of a very simple conflated temperature and heat, to the idea of just a one-to-one simple temperature model. The misconception that many students have of heat as substance or cold as substance that many I've taught have, and all the way through to be pushing them using the language of dynamic and statistical kinetic theory. Now, a big influence on my thinking in this as well was Tamer Amin from the American University of Beirut, who is, he's got huge amounts of psycholinguistic, he's a cognitive psychologist, but he's particularly interested in science education and the use of language in conceptual change. And so informed, I really suggest reading him about how the metaphors and analogies we use can either hinder or actually promote conceptual change. We'll see that in action in the experiments. Just to summarize his views, again, it was very interesting coming from a completely different viewpoint than Scheer and Adey, a different kind of research tradition. It overlapped so much what he found that by looking at transcripts of student discussion, this linear temperature concept at an early level, and then the substance idea, and then a few students at the end of secondary education moving much more to a dynamic and statistical systems approach. I thought this was really valuable insights, and in particular, as a teacher, using case methodology of how to help mediate student thinking. It reminded me very much of the way I learned German as a second language, that I would always ask the German teachers I worked with, I would always talk with them in German, and they would not point out my mistakes, they would not repeat my mistakes, but they would always mediate by actually continuing the conversation using the correct modeling. And I thought that was a very interesting concept. We're aiming for students, no matter what level they're at, to move towards this dynamic statistical systems thinking. Tamer Amin criticized a lot of the kind of secondary and early college textbooks that they kept using the substance concept, where they should have been moving much more towards dynamical statistical systems. Let's see how that plays out in the lessons. So I designed these lessons that have got these episodes that are called B for bridging, that again drop down to quite a low cognitive level. This is at the start of year 9. The students have had the preparation, they're familiar with the Piagetian schemata words. We've talked about concepts of equilibrium, we've talked about models. And so these lessons were designed to bridge onto that, to assume and keep on practicing the language of thinking, but within now the curriculum context of concepts of temperature and of heat transfer. The bridging also is, these lessons were designed to be about thermal equilibrium, where a reminder of lesson 28 and 30 in the case curriculum are dynamical physical equilibria, the uphill and down dale, as you can see, 28, which is to do with the 4 variables, to do with the different masses of the objects, the transport objects that come into equilibrium, and also the slope of the roads that they're on. And then lesson 30 is to do with lever law equilibrium, to do with balancing moments. So we have, again, 4 variables at work. We have, and relationships between these variables. So that was a starting point to focus back to the thinking that they'd done at the end of their case, at the end of year 8. So this bridging happened like this. These are very simple experiments, which is a major feature of CASE anyway, that it's not a hands-on inquiry style. It's a highly focused experiments that are designed to create cognitive conflict, to promote conceptual change. Very simple one was 2 equal volumes of water at different temperatures that would come in by a method of mixtures to equilibrium. And then the second episode would be different volumes, in this case a ratio of 2 to 1, at different temperatures. And this produces the kind of cognitive conflict where students with a very linear model of temperature, but no real concept that the mass or the amount of substance played a role. But there were students amongst the group who had that concept, which meant that cognitive conflict and social construction were really fruitful. Then it moves on to a much more challenging situation where we have 0 degrees Celsius water compared to 0 degrees solid ice. So back to the case methodology and how it applies here, that to create a cognitive conflict, we would always do some concrete preparation, getting the students to focus on what the key variables were. And the idea that we have volume as a variable or mass as a variable, that we have temperature beginning, we have temperature difference, and then we have temperature changes. And so a lot of the concrete preparation was making that clear so the students could make predictions, put forward explanations, which again is an opportunity to hear what their conceptual model of temperature and heat is. And in small group discussions, there would be a lot of cognitive conflict, and the results from the experiments would further keep that cognitive conflict alive. The social construction, throughout my application of case, and that's why I believe testing the students to know what Piagetian levels, I would always organize group work to maximize the range of cognitive conflict. So you would have students who would be arguing using their simple temperature model, simple linear model. There would be other students who have got a substance-based or caloric model of varying degrees of maturity, and occasionally some students who are already starting to connect to more kinetic models. So that's the pedagogy of case was applied within the conceptual change model specific to this curriculum area of thermal equilibrium. I've developed this in other areas like electricity, particle motion, diffusion, photosynthesis, but this is just an example of looking at the language demands that are highly content specific, domain specific, added together with the case language of creating cognitive conflict, of looking at variables, looking at equilibrium, what's needed. And so a constant rehearsal of the thinking demands. Okay, if you want to have a look at these lessons, they're online at these links. You can download the presentation. And we've been making an attempt to support case methodology, and I've put them on there. Any feedback will be really welcome. And so to summarize, CASE has produced a way of measuring the SRT, well validated across a wide range, so you can understand and you can either look at previous research or you can do this in your own classroom. I highly recommend it's worth the time to start before case lessons and towards the end of the case 30 lessons to do at least 2 of the SRTs. They are very much like a case lesson. They're very much within the skill set of a science teacher. You effectively demonstrate while they fill in the testing form. That's produced this mass of data to be able to look at the range across your school, across your department, compared to national norms. And also the CAT enables us to select and organize our curricula into a set of lessons that will bridge between and beyond the case lessons. Here's an example for the international school I worked at. We effectively built the first year of secondary program with lessons that were bridged in between the 15 case lessons we did with the year 7, or what we call grade 6. We continued with that all the way up to the pre-IGCSE that we used to do, and then we continued it when we did the International Baccalaureate Middle Years program. So this is an application of the principles of CASE, also the research about conceptual understanding. And I think the 2 of them can be well worked together. Okay, thank you very much. Yeah, I think that evaluation is really important. So if you can give me some feedback by clicking the link, If you want to download the presentation, it's there. And if you want to connect, there are my details. Thank you very much for your time.